I want you to picture the most advanced quantum computer you've ever seen in the media. Like, you know the exact image I'm talking about,
Oh,
right?
absolutely. It's that classic, that huge golden chandelier thing.
Yes, exactly. It's always this towering chandelier-like structure dripping with gold plating. And it's suspended inside these multi-million-dollar vacuum chambers. And, they're always surrounded by pristine clean rooms and cooled by massive dilution refrigerators to temperatures colder than deep space. So I want you to just hold that image in your mind, really look at it.
I mean, it really is the defining visual of the quantum industry right now. It's this monument to extreme engineering, and a very expensive one at that.
Right, and that's the key right there, the sense. So now I want you to completely erase that golden chandelier from your mind. Just totally wipe the slate clean. Instead, I want you to replace it with this. Imagine a small block of translucent sponge-like material.
Like a piece of frozen smoke, essentially.
Yeah, exactly like frozen smoke. It's about the size of a Rubik's Cube, and it's literally just sitting on a regular, everyday laboratory table. There's no golden chandelier. There's no billion-dollar clean room. Just, a little block of glass sponge.
Which is, frankly, a jarring visual contrast when you first think about it. But what you are looking at there is the physical embodiment of a complete paradigm shift. Because today we are doing a deep dive into version 1.3 of the Quantum Lattice white paper.
Yeah, and this paper, it's dated April 19th, 2026. For those following along, it completely blew my mind.
Right, because this document isn't just some theoretical physics paper. It is a highly detailed, highly strategic engineering roadmap. And it proposes a shift that, honestly, at first glance, feels almost absurd.
Totally absurd.
Yeah, they are talking about completely abandoning the flat, two-dimensional chips that have basically bottlenecked the semiconductor and quantum industries for decades, and instead pulling computing into a fully three-dimensional volumetric reality.
And the central promise here, the thing that literally made me stop dead in my tracks when I was reading through the sources, is the economics. I mean, they are projecting a path to drop the cost of a physical qubit by 1,000-fold.
By 3 orders of magnitude, yeah.
Which is insane.
Yeah.
They're targeting a cost of under 10 cents per physical qubit. 10 cents. And they claim they can manufacture this entire thing using a tabletop femtosecond laser setup. So our mission for this deep dive is to basically tear this white paper apart. We need to figure out, how current hardware is hitting a wall, and we need to unpack the actual chemistry of this frozen smoke matrix.
We also have to figure out how their graphene quantum dots can somehow operate at room temperature without, immediately falling apart.
Right, which seems impossible based on everything we know.
Mm.
And then finally, we'll trace their 5-year roadmap to an actual fault-tolerant network.
Yeah, so to really appreciate the solution here, we have to deeply understand the disease first. The authors state their core thesis right up front, which is quantum computing has not stalled because of the fundamental physics of superposition or entanglement.
Okay, so it's not the physics that's the problem.
No, not at all. It has stalled on a manufacturing problem.
So it's not that the science of qubits is failing us. It's that we literally just don't know how to build a factory that can make enough of them without bankrupting a small nation.
Exactly. Let's look at the dominant architectures that are trying to scale right now. You have superconducting transmons, so think of companies like IBM and Google there, and you also have trapped ions. Both of these modalities are currently slamming headfirst into what the paper calls a cost per qubit wall.
A cost wall. Because normally in tech, things get cheaper the more you make, right?
Right. In classical computing, we are incredibly used to economies of scale. Like, if a 100 transistor chip costs $1, a 4,000 transistor chip doesn't cost $10. It might cost, $1.10.
Yeah, because you just put them smaller.
Exactly. But in the current quantum paradigm, expanding a planar chip from 100 qubits to 1,000 qubits doesn't just cost 10 times as much. The white paper actually calculates it costs closer to 30 times as much.
I was really trying to wrap my head around that math when I read it.
Yeah.
Why does the cost curve bend the wrong way? If I'm buying in bulk, shouldn't my per unit cost plummet?
You're thinking about the raw materials of the chip itself, right? Which, yes, those do cost pennies. The actual silicon or sapphire wafer is cheap. The problem is the life support system required to keep those qubits alive.
Ah, the chandeliers.
Yes, the chandeliers. The infrastructure scales linearly and, in some cases, exponentially. To run a superconducting chip, you need a dilution refrigerator. These are magnificent machines. They use a mix of helium-3 and helium-4 isotopes to pull heat out of the system, dropping the temperature to literally a few millikelvin above absolute zero.
And those aren't exactly cheap, I imagine.
No, not at all. A single dilution fridge capable of housing a 1,000-qubit chip can cost anywhere between $400,000 and $2 million.
Wow. And you can't just keep stuffing more qubits into the same fridge, right? Because they all need wires.
Right. Every single qubit on a transmon chip requires its own dedicated microwave control line, running all the way from room temperature outside the fridge down to the millikelvin stage at the bottom.
That sounds like a plumbing nightmare.
It is. And each of those lines needs specialized cryogenic attenuators, filters, amplifiers, all just to ensure that room temperature thermal noise doesn't travel down the wire and destroy the delicate quantum state.
Okay, let me try an analogy here to ground this for everyone listening. Because building qubits on a 2D planar chip is kind of like trying to build a massive corporate headquarters, right? But you're only allowed to build 1 story high.
Oh, that's a good way to look at it.
Yeah, so you're spreading all the cubicles out on a single level across an entire city. And if you want to add more employees, you can't build up. You have to go buy more land, pave more roads, lay more horizontal plumbing.
And eventually, the cost of just acquiring the real estate and running all those utilities across that vast, flat distance becomes astronomical.
Exactly. So volumetric computing, this aerogel block the paper talks about, is basically the invention of the skyscraper. We are finally moving into the z-axis.
That analogy works exceptionally well because it highlights the dimension of density, right?
Yeah.
Volume scales as length cubed. So the paper proposes a reference device that is a 100 cubic centimeter block that's about 4.6 centimeters on a side.
Which is tiny. That fits in the palm of your hand.
Right. And if you are building a skyscraper inside that volume and you space your qubits roughly 100 micrometers apart in all directions, so up, down, left, right, forward, backward, you suddenly have roughly 100 million candidate qubit sites in the palm of your hand.
100 million.
Yes. That is a density profile that a 2D silicon wafer simply cannot physically accommodate.
But wait, I have to ask, if building a skyscraper is such an obvious solution to the real estate problem, why haven't the big players just done it? I mean, IBM has some of the smartest engineers on Earth. Why aren't they just building 3D superconducting transmons?
Because the physical rules that govern a transmon do not survive in 3 dimensions. You can't just stack them. We need to look closely at what a transmon actually is.
Okay, break it down for us.
It's essentially a microscopic electrical circuit made of superconducting metal, usually aluminum or niobium, and at its heart is something called a Josephson junction. This is a tiny nanometer-scale gap of insulating material right between 2 superconductors.
And that gap is where the magic happens.
Exactly. This junction creates the nonlinear energy levels that actually allow us to isolate a quantum state. But that tiny junction is incredibly sensitive to electrical noise.
And to protect it from that noise, they have to attach it to massive capacitors, right? I remember seeing pictures of them. They look like giant metal plus signs.
Yes, exactly. They build these macroscopic capacitor pads. Sometimes they're 50 to 500 micrometers across, and they use those to shunt the electrical noise and lower the charging energy of the circuit.
Okay, so they're huge compared to the actual junction.
Massive.
Yeah.
So imagine trying to pack these giant metal pads into a dense 3D volume. If you stack them on top of each other, they start talking to each other.
Crosstalk.
Right. The electromagnetic fields from one transmon's capacitor will bleed into the transmon sitting directly above or below it in the 3D grid. In 2D, you can space them out horizontally and shield them. But in 3D, that crosstalk just becomes a chaotic, unmanageable mess.
So they're basically just physically too fat to stack. What about the other major player, trapped ions? Those are literally single atoms floating in a vacuum. You can't get much smaller than a single atom. Why not stack those?
Trapped ions face a completely different but equally insurmountable geometric nightmare. To control a trapped ion, you don't use physical wires. You use precisely aimed lasers.
Okay, so light instead of wires.
Right. But if you arrange thousands of these ions into a dense 3D grid, the ions on the outside of the grid physically block the laser light from reaching the ions on the inside.
Oh, they literally cast shadows on each other.
Exactly. You cast shadows on your own qubits, you lose optical access. And there's another promising modality, neutral atoms and optical tweezers, but that requires complex real-time vacuum holography to hold the atoms in place.
Holography, like made of lasers.
Yes. And the paper notes that generating perfectly stable 3D optical traps across millions of sites in a vacuum It requires a level of laser power and control hardware that just scales horribly. It's essentially impossible at the millions scale.
So all the traditional approaches are fundamentally anchored to 2D by their own physics.
Yeah.
You can't just put a traditional foundation under a skyscraper. You need a completely new material.
You need a 3D scaffold.
Right. And this brings us to the most fascinating physical object I've read about in a long time. Silica aerogel. The frozen smoke. Let's really unpack this host matrix because it's wild. The paper says this 100 cubic centimeter block has a porosity of 95 to 98% and a density of less than 0.15 grams per cubic centimeter.
Which means, practically speaking, it is essentially 95 to 98% empty space. It is a solid object that is almost entirely composed of nothing.
And that emptiness is the feature, right?
Hmm.
Not the bug. Because it's mostly nothing, light can travel through it. It provides the optical access we need for our lasers to penetrate several centimeters deep into the block.
Yes, it solves the shadow problem the trapped ions had.
But I'm really struggling to understand the manufacturing here. How do you actually make a block of glass that is 98% empty space, yet somehow perfectly structured to hold quantum information?
This is where the chemistry gets deeply elegant. The technique they use is called bidirectional freeze casting, and it basically relies on controlling thermodynamics so precisely that you force nature to build the scaffold for you.
Okay, walk us through the kitchen. What exactly goes into the mixing bowl to make this stuff?
We begin with a chemical process called the sol-gel transition. You start with a precursor liquid, primarily something called tetraethyl orthosilicate, which is abbreviated as EO.
TEOS. Got it.
You mix that TEOS with water, ethanol, and an acid catalyst. When these mix, a chemical reaction called hydrolysis occurs. The water molecules basically attack the TEOS molecules, breaking off ethyl groups and replacing them with hydroxyl groups.
Okay, bit of chemistry class there, but I follow.
Then condensation happens. These new molecules start linking together, forming long branching chains of silicon and oxygen. This is the liquid becoming a gel.
So we are basically making a microscopic net of glass, and it's suspended in alcohol and water. But looking at the white paper, they don't just make glass. They add a very specific suspension of carbon-12 enriched graphene oxide, plus a polyamide precursor.
And that is a crucial step. Before the gel fully forms and locks up, they introduce the graphene oxide, which, spoiler alert, will eventually become our qubits, and the polyamide, which is a polymer that will eventually become our electrical wires.
So they mix the qubits and the wires into the soup before it even sets.
Yes. And the engineering challenge here is that all these vastly different chemicals must co-disperse perfectly. If the graphene oxide clumps together or if it phase separates, the whole block is ruined. It must be a perfectly uniform chemical soup.
Okay, so we have a perfectly mixed high-tech soup. Now we have to freeze it. But they don't just toss it in a standard chest freezer next to the frozen peas. They use, as you mentioned, a bidirectional freeze casting method. Now, I'm guessing bidirectional means freezing it from two sides, but why go through all that trouble? I mean, if I want an ice cube, I just freeze it from the outside in.
Well, if you put it in a standard freezer, the cooling is isotropic. It happens from all directions simultaneously, or it happens wildly unevenly based on air convection.
Right, the outside freezes first.
Exactly. So ice crystals will nucleate randomly on the edges of the container and grow inward in this chaotic, jagged mess. And when those ice crystals grow, they expand. They would shove the delicate silica and graphene oxide particles into a random disordered jumble.
Ah, so it would just ruin the structure. So bidirectional freeze casting tames that chaos. How exactly?
They pour the precursor soup into a specialized Teflon mold. And this mold is sandwiched between two Peltier-cooled copper fingers. These fingers are programmable thermal plates.
Okay, so precisely controlled cold plates.
Yes. They drop the temperature from minus 20 degrees Celsius down to minus 80 degrees Celsius at a glacial, strictly controlled rate of exactly 2 degrees per minute.
And because it's only cooling from the two opposing faces, those two copper fingers, the ice has to grow in a specific direction.
Exactly. The ice templating front grows inward from both sides simultaneously, meeting perfectly in the middle. As the water and solvents freeze into solid crystals, they naturally expel the silica, the graphene oxide, and the polyamide.
Wait, they expel them?
Yeah, the ice structure rejects the impurities. The growing ice literally sweeps the nanoparticles out of the way, packing them tightly into the spaces between the long columnar ice crystals.
Oh, wow.
And because the temperature gradient is so tightly controlled, it produces a highly uniform, symmetric, and radially aligned structure. The ice essentially forms microscopic straight tunnels.
So the ice itself acts as a temporary mold. It forces the glass and the carbon to form the walls of these tunnels.
That's exactly right. Nature does the heavy lifting.
But now, you just have a block of dirty ice, essentially. If you take it out and let it melt at room temperature, the liquid water would just slosh around and completely destroy the fragile glass structures you just painstakingly built.
Oh, absolutely. The capillary forces of liquid water evaporating would absolutely pulverize the nanopores. The surface tension of water is incredibly strong on a microscopic scale. It would pull the glass walls apart.
So how do you get the ice out without melting it?
To get the ice out, they perform sublimation. They place the frozen block into a vacuum chamber, drop the pressure to 0.1 millibar, and hold the temperature at minus 60 degrees Celsius for 48 hours.
A sublimation. Right, I remember that from high school physics. That's when a solid turns directly into a gas, skipping the liquid phase entirely, right? Like dry ice turning into fog.
Correct. The water molecules detach from the solid ice crystals and float away as vapor, and because there is never a liquid phase, there is no surface tension. The ice simply vanishes, leaving behind the empty silica skeleton.
That is so cool. But they don't stop there. The paper details a final step, which is supercritical CO2 drying. And I have to admit, supercritical fluid sounds like something out of a sci-fi reactor core. Let's slow down and really explain what a supercritical phase actually is.
It is a bit mind-bending. It requires looking at a phase diagram, which maps how a substance behaves at different temperatures and pressures. We all know solid, liquid, and gas, but if you take carbon dioxide and you raise its temperature above 31 degrees Celsius...
Okay, so reasonably warm.
And you simultaneously crank the pressure above 73 atmospheres.
Whoa, 73 atmospheres, that's intense pressure.
It is. You push it past what is called the critical point.
And what happens past the critical point? Does it become a liquid or a gas?
It becomes a supercritical fluid. The distinct boundary between liquid and gas completely disappears. It's a hybrid state. It acts like a gas, meaning it will expand to fill any container it's in. And importantly, it has zero surface tension.
Yeah, but it's not just a gas.
No, it acts like a liquid in that it has high density and can act as a solvent to dissolve things.
That is bizarre. It's a gas that dissolves things like a liquid.
It is deeply strange. So they take the fragile silica block, place it in a high-pressure chamber, and flood it with the supercritical CO2. The supercritical fluid easily penetrates deep into the microscopic pores, dissolving any residual alcohols or unreacted chemicals left over from the sol gel process.
It washes it.
Exactly. Then they simply vent the pressure. And because the fluid acts like a gas with zero surface tension, it gently escapes the pores without exerting any mechanical stress on the delicate glass walls.
Okay, I'm going to push back here. Hard. Because you are describing a block of glass that is 98% air, built around microscopic tunnels. Aerogel is famously fragile. I mean, we've all seen the YouTube videos where someone takes a piece of that blue aerogel and just crushes it to dust between two fingers.
Right, it shatters easily.
So how on earth does a sponge this fragile survive?
Yep.
Being handled in a factory, having lasers fired into it, and then eventually being cooled down to cryogenic temperatures. Wouldn't the thermal shock of dropping it to 4 Kelvin just instantly shatter it?
That is a highly valid engineering concern, and you're right to bring it up. The authors do not ignore it. In their risk analysis matrix, they heavily address the mechanical fragility of the silica framework.
So what's the fix?
Well, first, the freeze-cast process naturally creates thicker, aligned walls that give it a lot more structural integrity than a standard random aerogel. But it is still brittle. To mitigate this, they outline an optional chemical step: carbon nanotube, or CNT reinforcement.
Ah, so they are basically putting microscopic rebar in the concrete.
Essentially, yes. By incorporating ultra-strong carbon nanotubes into the initial sol gel formulation before freezing, the nanotubes weave themselves through the silica framework. It dramatically increases the tensile strength and the thermal shock resistance of the matrix.
So it holds it all together.
Right. This allows the block to survive vacuum environments, mechanical vibrations on the laser stages, and the extreme thermal cycling of a cryostat.
Okay, so we've solved the fragility problem. Now, why go through all this crazy chemistry? Why is a 3D block of pores better than a nice, clean, flat piece of silicon?
Because it changes the fundamental nature of how we build the computer. On a flat silicon wafer, placing qubits is a nightmare of lithography. You know, etching away material with harsh chemicals, aligning masks with literal atomic precision.
It's super tedious.
Extremely. Now, if you tried to do that in a free space 3D volume, placing qubits would be a stochastic problem, meaning it's random, chaotic, and incredibly hard to control.
Because you wouldn't know exactly where the laser's hitting in empty space.
Exactly. But this bidirectional freeze-cast geometry converts that chaotic problem into a deterministic one.
Explain that. How does the ice make it deterministic?
The pore structure itself becomes the grid. The lattice is already built for you by nature. The distance between the pores is determined by the speed of the freezing process. So you have this microscopic, perfectly aligned parking garage with millions of evenly spaced intersections.
Okay. Yeah.
The location of the qubit is no longer a random variable. It is strictly dictated by the intersection of the silica walls.
Okay, so we have an empty, perfectly aligned microscopic parking garage. But as we know, an empty parking garage doesn't compute anything. Now we need to talk about the cars, the qubits themselves, and the paper introduces graphene quantum dots, or GQDs. First off, scale this for us. What exactly is a graphene quantum dot?
A graphene quantum dot is a tiny isolated island of graphene. Now, graphene is a single layer of carbon atoms arranged in a hexagonal lattice. Think chicken wire, but made of carbon. When we say tiny, we're talking about lateral dimensions of just 2 to 20 nanometers across.
To give the listener a real sense of scale here, a single strand of human hair is about 80,000 to 100,000 nanometers wide. And we're talking about an object that is 2 nanometers wide. You can't exactly drop something that small into a glass sponge using a pair of tweezers. So how do we get these tiny graphene islands into our parking garage?
This brings us to the tabletop manufacturing process. The entire aerogel block is mounted on a highly precise motorized platform called a galvo and Z stage.
Okay, so it moves around mechanically.
Right. The platform moves the block under a femtosecond ultraviolet laser. Specifically, it's a laser firing at a 266 nanometer wavelength, pulsing extremely fast with incredibly low energy, just 40 to 100 picojoules per pulse.
Hold on, I need to visualize this, because I'm imagining a sponge made of glass. Sponges are cloudy. If I shine a laser pointer into a kitchen sponge, the light scatters everywhere, right? Which just diffuses into a glowing blob. How on earth do you target a specific microscopic intersection in a cloudy glass block? Wouldn't the laser light just hit a poor wall, scatter, and refract off into nowhere?
That is exactly the right physical intuition, but it comes down to the scale of the porosity versus the wavelength of the light.
Oh, the mountain saves us.
Exactly. The pores in this freeze-cast aerogel are roughly 5 to 20 micrometers wide. The laser light has a wavelength of 266 nanometers, which is much, much smaller than the pores. Furthermore, the silica struts themselves. The walls are much smaller than the wavelength of light.
So the light almost doesn't even see the walls.
Basically, yes. Because the structural features of the aerogel are vastly different from the wavelength of the laser, and because the silica itself is optically transparent, something called Rayleigh scattering is minimized.
So it doesn't blur.
Right. The laser can focus deeply into the volume with a high numerical aperture lens, creating a tight focal point deep inside the block without diffusing into a blur.
Okay, so the laser can reach deep inside the block without scrambling. But what does it actually do when it gets there? How does a laser create a physical dot?
Do you recall the graphene oxide we mixed into the original chemical soup?
Right, the stuff that got trapped in the walls of the pores when the ice formed. I was wondering what that was doing there.
Exactly. When the focused UV laser pulse hits a precise intersection of those pore walls, the intense photon energy triggers a highly localized chemical reaction called photoreduction.
Photoreduction, breaking things with light.
Yes. The UD photons carry enough energy to literally break the chemical bonds holding the oxygen molecules to the graphene lattice. The oxygen is stripped away, and what is left behind is a pristine, reduced, pure graphene quantum dot right there at the exact focal point.
That is mind-bending. You are literally nucleating a physical object, a working qubit, into existence inside a solid block of glass, using only light.
It is incredibly elegant.
But why use a graphene quantum dot? What makes this tiny island of carbon better at being a qubit than, say, a superconducting trans one?
It comes down to a physical principle called quantum confinement. In a normal, large sheet of graphene, electrons can move around freely. Graphene is a fantastic conductor. But when you take your laser and you reduce that graphene down to an incredibly tiny island, just a few nanometers across, the electrons are trapped. They physically don't have enough space to move.
Let me try to build a visual for that. Imagine a hyperactive dog running freely in a massive open field. It can run at any speed, in any direction. That's an electron in bulk graphene.
Good analogy.
Now, take that same dog and put it in a tiny cramped crate. The dog's behavior fundamentally changes. It can only pace a few inches. its energy states become completely restricted by the physical walls around it.
That captures the essence of it perfectly. In solid-state physics, we say that this spatial confinement alters the electronic structure and opens up a band gap.
Okay, break down band gap for us. What does that mean for the computer?
In a material, electrons occupy energy levels called bands. The valence band is where electrons are normally sitting, bound to their atoms. The conduction band is a higher energy level where electrons are free to move and conduct electricity.
Like the open field.
Exactly. In bulk graphene, these two bands touch. There's no barrier. But when you confine the graphene into a tiny dot, a gap opens up between them. The electrons need a specific, discrete burst of energy to jump across that gap. In these GQDs, the band gap is roughly 1 to 3 electron volts.
And why is a 1 to 3 electron volt band gap useful for a quantum computer?
Because it creates highly localized, discrete energy states. At the jagged edges of this tiny graphene island, or at specific defects within its lattice, you get sparse, unpaired electrons.
Single electrons just sitting there.
Right. And because of the band gap and the confinement, the spin of that single unpaired electron is isolated and protected. We use the quantum spin of that electron whether it is pointing up or down as are 0 and 1. And because it's localized in this rigid carbon lattice, its properties are highly predictable.
So instead of needing a giant 500 micrometer metal capacitor pad to wrangle a quantum state, the tiny physical walls of the dot force the electron's spin into a usable, isolated form.
Yes, the material does the work for you.
But the paper makes a massive, industry-shaking claim here. I really want to dig into this. They state that these electron spins have long coherence times at room temperature. Everything I've ever learned about quantum computing says that thermal noise, just the ambient heat of the room, will instantly scramble a delicate quantum state. How is room temperature even physically possible here?
This is perhaps the most elegant piece of physics in the entire architecture. It hinges entirely on the specific isotopes of carbon they use.
Isotopes. Okay, let's get into it.
Let's look at naturally occurring carbon. If you dig up a chunk of graphite, about 98.9% of it is carbon-12, but the remaining 1.1% is an isotope called carbon-13.
Okay, and an isotope just means it has an extra neutron in its nucleus. Why does one extra neutron matter to our quantum computer?
It matters immensely because a property called nuclear spin. Carbon-12, because it has an even number of protons and neutrons, has a nuclear spin of 0. It is magnetically silent. It doesn't generate any magnetic field whatsoever.
It's perfectly quiet.
But carbon-13 has an odd number of neutrons. It has a non-zero nuclear spin. It acts like a tiny fluctuating bar magnet.
Okay, I think I see where this is going.
In a normal piece of carbon, that 1.1% of carbon-13 creates a chaotic, constantly shifting magnetic environment. We call this the nuclear spin bath.
I want to make sure the listener is really visualizing this.
Yeah.
Is the nuclear spin bath like trying to have a quiet conversation in a crowded, noisy restaurant?
Let's make the analogy even more precise. Imagine you are trying to listen to the incredibly faint, rhythmic ticking of a single perfect pocket watch. That delicate ticking is the spin of our localized electron qubit.
Yeah.
Now imagine you are placed in a room with 100 metronomes. 99 of those metronomes are completely broken. They have no pendulums. They make absolutely no sound. That's the carbon-12.
So 99 of them are quiet.
Right, but one of them, the carbon-13, is ticking wildly, loudly, and completely out of sync. That one erratic metronome generates enough acoustic noise to completely scramble your ability to focus on the pocket watch. That is the nuclear spin bath. The erratic magnetic fields from the carbon-13 flip the electron spin randomly, destroying the quantum state.
Man, that is a great analogy. So if 1.1% of the carbon is noisy metronomes, how do they fix it? Do they just turn the metronomes off somehow?
You can't turn them off. You have to remove them before you even build the room.
Oh.
The quantum lattice protocol dictates that they start with highly enriched carbon-12. Through advanced isotope separation techniques, they deplete the naturally occurring carbon-13 down to less than 0.01%.
So they painstakingly filter out the noisy carbon metronomes before they even mix the precursor soup for the aerogel.
Precisely. By doing so, they create a nuclear spin bath that is functionally empty. There is almost no background magnetic noise. Without that interference, the delicate electron spin is protected from magnetic decoherence.
And that's what gives them this stability.
Yes. The paper notes that measured T2 star values, which is the Ramsey coherence time, a measure of how long a superposition state survives, already reach between 1 and 10 microseconds at 300 Kelvin, which is room temperature.
1 to 10 microseconds might sound incredibly fast to our listeners, but in the quantum computing world, that's an eternity. That's more than enough time to actually execute logic gates.
Exactly.
But here is the next logistical nightmare that popped into my head reading this. The paper says these dots have all electrical control. We have 30,000 isolated, highly coherent quantum dots sitting in their microscopic parking spaces. But they are surrounded by an electrically insulating glass sponge. How do we actually send electrical signals to them? We have to wire up a 3D block of fragile glass without breaking it.
You use the exact same tabletop factory. This is where the paper introduces laser-induced graphene, or LIG, interconnects, and this is where the vertical integration of this process really begins to shine. We don't have to take the block out of the machine.
Wait, really? It just stays on the stage?
We don't have to move it to a clean room to apply photoresist or etch metal. We keep the aerogel block exactly where it is, on the exact same galvo stage.
Okay, so we use the ultraviolet laser to nucleate the qubits. Now what?
The system simply switches to a different laser head. It uses a high-fluence infrared laser, specifically operating at a 1030 nanometer wavelength. It pulses with a higher energy than the UV laser, between 1 and 10 microjoules per pulse.
Okay.
Now, do you recall the polyamide precursor we mixed into the original soup?
Right. The polymer that got trapped alongside the graphene oxide? I was wondering when that was going to become useful.
The IR laser scans through the 3D volume, specifically targeting the regions coated in that polyamide. The intense localized heat from the high-fluence infrared pulses doesn't melt the glass. Instead, it carbonizes the polyamide.
It burns it.
It breaks down the polymer chains, boiling off the non-carbon elements as trace gases, and leaving behind a continuous, highly conductive trace of carbonaceous material. It is literally drawing electrical wires made of graphene directly into the aerogel matrix.
You are drawing 3D electrical wires with light inside a solid object. That is wild.
It's revolutionary manufacturing.
But hold on, if we have 30,000 qubits, do we need 30,000 wires routing to the outside of the block? That sounds like a complete rat's nest.
Yeah.
How do you fit 30,000 wires on the surface of a block the size of a Rubik's Cube?
You don't. The laser scans a pre-designed fan-out network that uses multiplexing.
Okay, multiplexing.
It gives each individual graphene quantum dot a microscopic local LIG pad, which acts as a gate for applying voltage, and a shared II bus, which acts as a ground. These traces route outward through the complex 3D volume, converging into roughly 12,000 input-output pads, terminating across the 6 external faces of the cubic block.
Okay, so it's spreading the connections across all 6 sides of the cube, averaging about 2,000 pads per face. And to interface those tiny microscopic carbon traces with the massive macroscale control racks that actually run the computer, they use commercial low-temperature co-fired ceramic or LTCC interposers. But wait, if they have 30,000 qubits, how do 12,000 I/O pads control them all? The math doesn't add up there.
The design assumes that each qubit is not independently DC biased with its own dedicated wire. Instead, they are addressed through frequency multiplexing on shared transmission lines.
Ah, okay. Let's explain multiplexing for the listener. Is it basically like tuning a radio?
Very much so.
Right.
Imagine a single radio tower broadcasting multiple stations simultaneously. The signals are all traveling through the exact same medium in the air, but they're at different frequencies. Your car radio uses a tuner to isolate just the 99.5 megahertz frequency, ignoring all the others.
So we are sending a bunch of frequencies down one wire.
Right. In the quantum block, we send a complex microwave pulse containing multiple frequencies down a single LIG wire. The local geometry of each qubit's local LIG pad acts as a microscopic tuner. It only responds to its designated frequency, allowing us to control multiple qubits with a single external wire.
That is incredibly efficient. Okay, this brings us to the economics, because this is where the paper really throws down the gauntlet. By using this tabletop laser setup to do everything, nucleating qubits and drawing wires, they are trying to bypass the billion-dollar clean room entirely. And the bill of materials they lay out is staggering. Let's just look at the capital expenditure.
See, CapEx is the real shocker here.
They list the core laser setup, a light conversion Ferros IR laser at about $145,000, and a spectrophysics UV laser at $105,000. When you add in the motorized stages, the microscopes, and the control electronics, the total upfront cost for this entire factory is roughly $930,000.
And if a research lab wants to run these blocks at extreme ultra-cold temperatures for maximum performance, they add an optional dilution fridge for about $400,000. That brings the total capital expenditure to roughly $1.35 million.
A traditional quantum fab costs hundreds of millions of dollars. 1.35 million is a rounding error for an industrial research lab, like pocket change. And then there are the consumables, the actual materials that get used up every time you print a block.
The raw material cost is absurdly low.
Let's read them off. The TO's chemical is about $80. The highly purified carbon-12 graphene oxide is $240. The polyamide is $60. The liquid CO2 and inert gases for the drying add another $34. The total consumable cost for raw materials is exactly $414 per block.
And if that block yields 30,000 functional physical qubits, your raw material cost is approximately 1.4 cents per qubit.
1.4 cents.
Even when you model the depreciation of the million-dollar laser system over a 5-year useful life, and you factor in electricity and technician labor, the fully loaded cost falls well under their target of 10 cents per physical qubit.
The phrase that jumped out at me in the text was zero marginal fabrication cost. And I really, really want to emphasize this for you listening. If you are a traditional company building a planar superconducting chip and you decide you want to upgrade your 100 qubit model to a 30,000 qubit model, you have to go completely back to the drawing board.
It's a complete redesign.
You have to invent entirely new lithography techniques to shrink the components. You have to physically build a wider silicon wafer, and you have to buy a massive new dilution fridge that can physically hold the larger chip. The costs just skyrocket with every added qubit. But with this volumetric aerogel method, the rules change entirely.
Because the volume is already there, the empty space is already waiting.
Exactly. Once you lock that 100 cubic centimeter block inside the laser chamber, writing 100 qubits costs exactly the same amount of money in materials and overhead as writing 30,000 qubits.
The only variable that changes is time. The femtosecond laser doesn't care how many sites it addresses, it just pulses. The throughput is limited strictly by the physical speed of the galvo mirrors scanning the beam and the repetition rate of the laser itself.
So how long does a block actually take to print?
The authors provide a detailed time budget. It takes roughly 10 minutes for the UV laser to nucleate the 30,000 qubits. It then takes another 3 hours for the IRR laser to scan and write the 5 million pulses required for the complex LIG electrical interconnects. When you add in calibration and stage movement, the entire active write time for a 30,000 qubit processor is about 8.5 hours.
That's a single workday. You walk into the lab in the morning, you hit print on the laser, and by the time you leave for dinner, you have a newly minted 30,000 qubit processor sitting there. It's astonishing.
It really is.
But the electrical wiring, the LIG traces, are just the first layer of communication. The architecture utilizes a second, completely hidden network written entirely with light. This part absolutely blew my mind. They detail a 3D optical processor.
This is where the architecture ruthlessly exploits the optical transparency of the silica aerogel. As we noted earlier, the freeze-cast structure minimizes Rayleigh scattering. So after the LIG wires are drawn, the exact same IR laser makes a third and final pass through the block.
Wait, I have a question here. If they fire the infrared laser into the block again, won't it just hit the remaining polyamide, burn it, and create messy, unintended carbon wires everywhere?
That would happen, except they alter the laser parameters. They drop the energy density of the beam vastly. They lower it down to between 0.05 and 0.3 microjoules per square centimeter.
So it's a much weaker beam. It doesn't have the punch to burn the polymer.
Exactly. At this low energy level, the laser is way below the ablation threshold. It doesn't have enough heat to carbonize the polyamide or vaporize the glass. Instead, the rapid succession of weak femtosecond pulses causes a very localized melting and rapid quenching of the silica nanoparticles.
Localized melting. So it's essentially squishing the glass structure together slightly.
We call it densification. By slightly melting the porous struts, they collapse slightly, increasing the local mass density of the silica along the precise path the laser travels. And in optics, there is a fundamental rule. When you increase the density of a transparent material, you raise its refractive index.
The refractive index, that's how much the material bends light, right? Like when you look at a straw in a glass of water and it looks broken.
Correct. The paper states this densification process creates a refractive index contrast, a delta N of about 0.01 to 0.1 between the laser scan path and the untouched aerogel around it.
Okay, so a small difference in how light bends. Why does that matter?
That contrast is critical. Because the scanned path has a higher refractive index, light injected into that path will undergo total internal reflection. It bounces off the lower index aerogel boundaries and stays completely trapped inside the path.
Oh, they're literally drawing 3D single-mode photonic waveguides, Basically fiber optic cables directly into the block.
Exactly. They are sculpting waveguides out of the glass sponge itself.
So they're building fiber optic cables out of thin air, out of glass sponge, right
Mhm.
inside the block, just by changing how dense the glass is. What do these optical pathways actually do for the computer?
They serve as a high-speed communication backbone. They connect arbitrary pairs of graphene quantum dots across the volume of the block. We discussed earlier how the localized electrons in the GQDs act as spin qubits, but these dots can also emit single photons when excited.
Right. The paper mentions single photon emission with radiative lifetimes of a few nanoseconds.
The densified waveguides capture those emitted photons. This creates an optical spin-photon interface, allowing the quantum state of an electron's spin to be transferred to a photon, whisked across the block at the speed of light, and entangled with a completely different qubit.
That's incredible. And they aren't just drawing straight lines, right?
Oh, no. The paper lists specific addressable photonic structures they can write. Y-splitters, which take one photon pulse and distribute it to many sites for clock synchronization. Mach-Zehnder interferometers, which split a photon and recombine it to measure phase shifts. And ring resonators, which act as microscopic filters to tune specific wavelengths of light. All of this operates in the 1000 to 1550 nanometer telecom band, with signal losses below 2 decibels per centimeter.
And because it's a true 3D volume, they can route these fiber optics in 3D space. On a flat silicon photonic chip, if two light paths need to cross, it's an engineering nightmare of layer stacking. In this block, a waveguide can just swoop over or under another waveguide without touching it.
The topological flexibility is immense, and this dual network, having both electrical wires and optical fibers, provides two distinct readout modalities for checking the state of the qubits.
Right, checking the state. How fast can we get an answer out of this machine? Because speed is everything.
The electrical LIG layer, using standard dispersive microwave techniques at 1 to 10 gigahertz, has a readout latency of about 100 nanoseconds per qubit. That's fast enough for standard operations. But the optical layer uses components called superconducting nanowire single photon detectors, or SNSPDs.
Try saying that 5 times fast.
Right. These SNSPDs are mounted on the outer optical facets of the block. When a single photon hits the nanowire, it disrupts superconductivity, creating a measurable voltage spike. This optical readout achieves a blazing latency of just 10 nanoseconds per qubit.
10 nanoseconds. So to compare this to a city's infrastructure, the electrical LIG traces are like the paved roads for local traffic. They get you to every single house, but the speed limit is 30 miles an hour. But these photonic waveguides are like high-speed fiber optic subway trains, darting directly through the subterranean volume of the city, bypassing all the surface traffic to deliver critical signals almost instantly.
A very apt comparison. The control software can dynamically choose whether to use the roads or the subway depending on what operations are executing at that exact microsecond. This redundancy dramatically enhances reliability.
Okay, so we have an incredibly complex city, 30,000 qubits connected by both carbon wires and light paths. The scale is massive, but anyone who knows quantum computing knows that quantum states are incredibly fragile. I mean, they are prone to errors from the slightest bump in temperature, a stray magnetic field, or just spontaneous decay. How does this architecture keep 30,000 fragile items perfectly synchronized and free of errors?
To understand error correction, we first have to understand the manufacturing yield. In any fabrication process, whether it's building cars or computer chips, not every single component comes off the line working perfectly. You have defects.
Sure, nothing is 100%.
Right. Out of the hundreds of millions of potential sites in the block, the control system targets a widely spaced subset of 30,000.
But they can't assume all 30,000 will work, so they use a Monte Carlo yield model to predict the failure rate. Let's dig into that. For the listener who hasn't taken advanced statistics, what exactly is a Monte Carlo simulation?
A Monte Carlo simulation is a mathematical technique used to understand the impact of risk and uncertainty. Imagine you want to know the odds of rolling a total of 7 with 2 dice. You could calculate the complex probability math, or you could just program a computer to roll virtual dice 10,000 times and count how many 7s you get. The simulation runs thousands of randomized trials based on known probabilities to predict an overall outcome.
So they ran 10,000 virtual dice rolls for building a 100 cubic centimeter block.
Yeah.
What were the dice that were rolling? What are the ways a single qubit site can fail in this manufacturing process?
They modeled 4 distinct failure modes as independent Bernoulli trials, meaning each site either passes or fails based on specific odds. First, a GQD nucleation miss. There is an 8% chance that the UV photon hits the pore wall at a weird angle and fails to cleanly sever the oxygen bonds, meaning the quantum dot doesn't form correctly.
Okay, so 8% chance the dot just doesn't print.
Right. Second, a Leydig trace open. There's a 3% chance that the polyimide precursor was locally too thin, and the laser fails to draw a continuous electrical wire. Third, a 2% probability of photonic waveguide failure, where local density variations cause the optical signal to scatter too much.
And the fourth.
A 4% chance of correlated failure due to a macrostructural flaw in the aerogel itself, like a microfracture from the freeze casting.
So if any one of those four things happens, a bad dot, a broken wire, a leaky fiber optic, or a cracked wall, that specific qubit site is basically declared dead by the software and ignored.
Correct. A site is only mapped as functional if it passes all four probability checks. Across the 10,000 Monte Carlo trials, the model predicts a mean and median yield of 30,040 functional physical qubits out of a slightly larger targeted batch.
So they aim a little higher to guarantee the 30,000.
Yes, even at the 5th percentile, which is the absolute worst-case conservative bound where everything goes wrong, they still yield 19,520 perfectly functional physical qubits. At the 95th percentile, they hit over 40,000.
So mathematically, they have extreme confidence they will get a stable floor of roughly 30,000 working qubits. But we need to make a critical distinction here. Physical qubits are not the end goal, because physical qubits, even good ones, are noisy. They make mistakes.
Yeah.
To do real math, we need logical qubits.
This is the crux of the entire industry right now. How do we translate physical yield into fault-tolerant computational power? The answer the white paper relies on is the surface code.
The surface code. It's a type of topological quantum error correcting code. Let's build an analogy for this because it's heavy stuff. Think of a physical qubit, like a single singer in a choir. If that one singer is asked to carry the entire melody alone, and they suddenly cough or forget the lyrics or hit a flat note, the entire song is ruined. That's a calculation error.
I get this.
But if you group 50 singers together and tell them all to sing the exact same note in unison, they act as one single powerful voice. If one person in the back row coughs, the other 49 singers easily overpower the mistake. The song, the data, survives intact. That unified group of 50 physical singers acting as one, that is a logical qubit.
That analogy perfectly illustrates the concept of redundancy and fault tolerance. But the surface code is even smarter than just having everyone sing the same note. It involves a massive checkerboard grid of qubits. Half of them are data qubits holding the information, and the other half are ancilla, or measurement qubits.
Okay, so what do the measurement qubits do?
The measurement qubits constantly check the relationship between their neighboring data qubits without actually reading the data itself, which is important because reading it would collapse the quantum state.
Right, because if you look at a quantum state, it breaks. So they ask roundabout questions like, hey, are my two neighbors currently in the same state or different states? Without asking what the state actually is.
Exactly. And by constantly pinging the grid with these parity checks, the software can track when a bit flips accidentally and mathematically correct it before it ruins the calculation. The paper breaks down the math of how many physical qubits you need to form one of these indestructible logical qubits based on something called the code distance, represented by the letter D.
I want to slow down and check in with the listener here.
Yeah.
If you are driving right now or maybe folding laundry while listening, don't worry about writing this formula down. We'll walk through the math together.
The formula for a rotated planar surface code is that it takes roughly 2 times squared minus 1 physical qubits to create one logical qubit. The distance essentially defines how many simultaneous errors the logical qubit can absorb without failing.
Okay, let's run the numbers. The paper targets a code distance of D equals 5. 5 squared is 25, times 2 is 50, minus 1 is 49. So it takes an array of 49 physical qubits, our 49 singers, to make one stable logical qubit.
Precisely. So if you take our median yield of 30,040 functional physical qubits on the block, and you divide by 49, you get approximately 612 logical qubits. If you account for routing and shared ancillas, it settles around 600.
600 logical qubits from one block.
Now, if you want even stronger error correction for a highly complex algorithm, you move to a distance of D equals 7.
Okay, let's do that math. 7 squared is 49, times 2 is 98. Minus 1 is 97 physical qubits per logical qubit. And 30,040 divided by 97 gives us roughly 310 logical qubits.
Which is staggering. To give you context, current state-of-the-art quantum computers are struggling to demonstrate just a handful of logical qubits. A single block producing over 300 perfect, fault-tolerant logical qubits would shatter every current benchmark in the industry.
It would rewrite the textbook.
But there is a catch. To run these surface codes, the qubits have to maintain their coherence. They have to stay perfectly in tune long enough for the ancilla qubits to run their checks and for the classical software to calculate the corrections.
We mentioned room temperature earlier, getting 1 to 10 microseconds of coherence. The paper says a single surface code cycle takes about 10 microseconds to execute. If your coherence time is identical to your cycle time, the qubit is decaying right as you finish measuring it. You aren't actually getting ahead of the errors.
Right, it's borderline unusable for deep algorithms at room temperature. This is why Section 7.3 highlights the scaling of coherence with temperature. While they can operate at room temperature for basic sensing for fault-tolerant computation, they cool the block down.
If they drop it in liquid nitrogen at 77 Kelvin, the coherence jumps to 50 to 500 microseconds. But if they place it in a standard liquid helium cryostat at 4 Kelvin,
the electron spins freeze out almost all remaining phonon interactions, which are physical vibrations in the lattice. The coherence time leaps to a massive 0.5 to 5 milliseconds.
So at 4 Kelvin, the qubit state survives for 5,000 microseconds.
Yeah.
And the error correction cycle only takes 10 microseconds.
Exactly. The qubit easily survives through hundreds of error correction cycles before naturally decaying. This places the logical operations well below the mathematical threshold for fault-tolerant scaling. It's a comfortable, highly stable operating regime. And the crucial point is that they achieve this extreme stability at 4 Kelvin.
And 4 Kelvin is standard cryogenics. You don't need a $2 million dilution fridge to reach 4 Kelvin. You can buy a commercial liquid helium system for a fraction of that cost.
It's very accessible technology.
But this brings up another massive logistical problem. It's one thing to have the Aerogel hardware physically pinging parity checks, but tracking the microscopic errors of 30,000 qubits, updating the math every 10 microseconds, that is an unfathomable torrent of data. Can standard classical computers even keep up with decoding that fire hose of quantum errors in real time?
It's a massive challenge called the decoding bottleneck. A few years ago, the classical computing overhead would have choked the system entirely. But the paper points to a critical software convergence. Surface code decoders, the algorithms that figure out what error happened based on the parity checks, have recently been highly optimized.
Optimized how? Like better code?
Better hardware alignment. They move them off slow CPUs and onto consumer-grade GPUs graphics processing units.
Wait, like the graphics cards teenagers use to play video games?
Exactly the same. The highly parallel architecture of a GPU is perfectly suited for tracking thousands of simultaneous surface code patches. The control stack explicitly relies on open architecture decoders running on off-the-shelf NVIDIA or AMD hardware, achieving millisecond scale latency.
So they aren't inventing a new multi-million-dollar classical supercomputer to run the quantum computer. They're just plugging it into server racks you could buy today.
Yes, it's incredibly pragmatic.
So let's step back and look at the big picture. The math for the surface code proves it works on paper. The lasers and chemicals exist on the market today. The cooling requirements are standard and cheap. The software can run on consumer GPUs. The pieces are all there. So what is the exact timeline for actually building this?
The authors lay out a heavily scrutinized, risk-weighted 5-year engineering roadmap. It is a 54-month schedule with an incredibly lean budget of $18 to $24 million.
It's $18 million.
Yeah.
AI startups raise that in a seed round just to build a chatbot. And they want to build a fault-tolerant quantum computer for that.
Because the capital expenditure is so low, they don't need to build a factory. They just need to buy the lasers. The roadmap covers Phase 0 to Phase 5. Phase 0 is the immediate proof of concept. They allocate 3 months and $250,000 to build a tiny 1 cubic centimeter aerogel block with just 300 GQD sites. The goal is solely to verify nucleation and measure photoluminescence.
Then Phase 1 scales to a 10 cubic centimeter block with 3,000 qubits, proving they can hit that 1 microsecond room temperature coherence and confirming the electrical LIG readout works. Then we hit the inflection point, Phase 2 and 3.
This is scaling up to the 100 cubic centimeter reference block we spent the hour dissecting, 30,000 physical qubits, integrating the 3D photonic waveguides. By the end of Phase 3, the milestone is demonstrating a fully stable D equals 3 logical qubit on a single block,
which opens the door to the endgame. Phase 4 aims for full fault tolerance using the D equals 5 surface code patch we calculated earlier, and Phase 5 is where the architecture reveals its ultimate potential, modular networking.
Because they have those optical waveguides terminating at the outer facets of the block, they can seamlessly link multiple blocks together. They just plug standard telecom optical fibers into the SNSPD interfaces. They can network the processors across a server rack.
So if one aerogel block is a skyscraper, Phase 5 is building an entire interconnected skyline of skyscrapers, linked by high-speed fiber optic bridges. That brings us to the so what of all this, the applications. In the near term, if you only have a single block yielding 100 logical qubits, what can you actually sell? What does it do?
The paper specifically highlights the quantum simulation of molecular systems. Classical computers, even supercomputers, choke when trying to simulate the complex quantum interactions of molecules. But a machine with 100 logical qubits operates using those exact quantum mechanics.
It speaks the language of molecules.
Exactly. It would be genuinely disruptive for discovering new catalysts for clean energy, improving photovoltaics for solar panels, and developing complex small molecule pharmaceuticals.
So immediate commercial value in chemistry. But the medium-term applications are what keep intelligence agencies up at night. They mention cryptographically relevant quantum computing, specifically running Shor's algorithm.
Shor's algorithm is a quantum algorithm that finds the prime factors of an integer.
And prime factorization is the entire bedrock of modern digital security, right?
Yes. The RSA 2048 encryption that secures everything from your bank account to classified military communications relies on the fact that classical computers take thousands of years to find the prime factors of a massive number. A sufficiently large quantum computer using Shor's algorithm can find them in hours.
That's terrifying.
But doing so requires an immense amount of error-corrected logic. The paper notes that breaking RSA 2048 requires roughly 20 million physical qubits under standard surface code assumptions.
20 million. Now, let's do the math on the network. A 20-block network,
Yeah.
just 20 of these little aerogel Rubik's Cubes wired together in a rack would yield about 30 million physical qubits.
Which translates to roughly 600,000 highly stable logical qubits distributed across the network. That is well beyond the threshold for cryptographically relevant computing. As the authors state, it is an aggressive target, but the math fully supports it. The scaling limits are modular, not physical.
Before we wrap, I want to touch on the business strategy they mentioned, their defensible moats. Because this entire process uses commodity chemicals like TOs, ethanol, and CO2, and uses off-the-shelf commercial lasers. You can't really patent the raw materials. I could buy the lasers tomorrow if I had the cash.
You could, but you wouldn't know how to run them. The real intellectual property isn't a single magical patent on a chip. It's the vertical integration of the chemistry, the thermodynamics, the laser fluences, and the software. It's the deep process know-how. The authors compare it to TSMC in the silicon world.
Right. TSMC doesn't own the concept of a transistor, but nobody else on Earth knows exactly how to tune the massive lithography machines to yield nanoscale transistors at a 99% success rate. The secret sauce is the recipe, not the ingredients.
And because the capital expenditure is around $1.5 million per tabletop pilot line, it completely circumvents the legacy gatekeepers. It supports a distributed open architecture model. University labs, mid-sized research institutes, and startups can afford to buy the lasers, build the blocks, and contribute to refining the network.
It democratizes the hardware.
It fosters a massive network effect that legacy competitors who are burdened by the need to build billion-dollar megafabs simply cannot replicate or pivot to quickly.
So let's step back and summarize the incredible journey we've taken today. We started by looking at the towering, gold-plated chandeliers of modern quantum computing and realized that their fundamental bottleneck isn't the mysterious physics of superposition. It's a mundane manufacturing problem. They are trapped in 2D space.
Absolutely trapped.
We explored how the quantum lattice white paper proposes abandoning the flat silicon chip for a volumetric 3D silica aerogel block. We unpack how bidirectional freeze casting builds a microscopic, highly uniform parking garage out of ice and glass.
Using nature to do the building?
We saw how a single tabletop femtosecond laser uses UV light to nucleate pristine graphene quantum dots, and then uses IR light to draw both carbon electrical wires and dense fiber optic pathways directly into the empty space.
All in the same machine.
By moving into the z-axis, the industry can collapse the per-qubit cost by 3 orders of magnitude, dropping it under 10 cents a qubit. And by combining massive physical yields with the topological surface code running at a cheap 4 Kelvin, they are charting a highly realistic path into the fault-tolerant era of quantum computing.
It is a true paradigm shift, challenging the deepest assumptions of how computers must be built. And it leaves us with a profound realization to ponder. Consider what it means when processing power is no longer tied to the two-dimensional surface area of a silicon wafer. Processing power becomes a volumetric property of empty space and sculpted light.
Volumetric empty space.
If we can encode a cryptographically powerful supercomputer, a machine capable of breaking global encryption and simulating molecular reality into a single hand-sized block of frozen smoke, the ultimate limit to human computation won't be how much rare earth we can mine or how many billion-dollar cleanrooms we can build. It will simply be how intricately we can fold our ideas into the empty dimensions around us.